in my email something from physics division saying, oh, we don't have a colloquium on Friday. Why don't you guys just go over and listen to Linda's talk today? And someone even, Jerry Nolan even offered to take people in his van. So that really surprised me. But it just goes to show you can never quite escape your roots, because they were so nice to hire me into their division as assistant scientist a long, long time ago. And so now, I've traveled all around the lab. And now, although the AMO group is over in CSE, we actually still reside here. And let me show you the members of our group. There are quite a few of us actually here, because some of the people here have, let's see, I guess they've become what in physics division is very common, an STA, the people who come back to work and offer all their wisdom without really being paid properly. But anyway, so Bob Dunford I saw was here, and then of course Elliot Cantor, who is missing from this photo, but he's also one of the STA in the AMO group. Also, I wanted just to point out, since we all live in this building, that you guys here from APS will see us around. And a new face that you may not recognize here is Christoph Bosted, who just joined us from SLAC and is the new group leader for AMO Physics. And so he's somewhere here in the audience, but over there. Okay, so it's kind of hard to figure out what to talk about in some sense, because you want to pick some you can't talk about everything, but you want to pick some topics that you think are sort of interesting to the audience at hand, and so that's what I tried to do. And so I wanted to start off with this. Most of you in the audience are familiar with this, that in 2014 it was the International Year of Crystallography. And that celebrated the centennial of the Nobel Prize to von Laue for discovering X-ray diffraction from crystals. And so what happened was Nature made this nice booklet called Milestones in Crystallography. And so they have all these nice milestones, but what was interesting was the very last milestone in this was this, X-ray free electron lasers. That was the very last milestone in 2000. And with it, they showed this nice picture, seeing in a flash, which actually comes from one of the very first publications from the LCLS by Marvin Siebert and his collaborators, most notably János Hajdú, which basically says, oh, well, maybe we don't need crystallography at all. Maybe we can do without crystals. And that is kind of some of the motivation behind what we do in AMO physics, is trying to understand if that is in fact possible. Okay, so what are free electron lasers? Okay, in this audience it probably does not need any discussion at all, but I do want to show this to you because it compares accelerator-based sources here on the left with laser-based tabletop sources on the right. And both have had a very dramatic improvement over the last, some years. So on the left, you see here, and I want to compare for this particular, application. So here on the left, what we have is X-ray brilliance, brightness as a function of year. And what you see is, this very fast exponential rise. And the rise, here is APS, and these are the standard units of photons per second per square millimeter per milliradian per 10% bandwidth. But here's the APS, and then these free electron lasers, for which that milestone in crystallography was talking about, are up here by another several orders of magnitude. If you actually looked at peak power, peak brilliance, it would actually be greater by 9 orders of magnitude. I mean, 1 billion times greater. So that's really, rather fantastic, especially if you're looking at fundamental interactions between matter and X-rays. And so for one of these sources, LCLS, that was the first hard X-ray free electron laser, you get numbers like this per pulse. 10 to the 13 X-rays per pulse per 1% bandwidth at a keV, roughly in 100 femtoseconds. 10 to the 13, that's the number to sort of remember. It's a huge amount of flux in 100 femtoseconds. You might get that in a second here at the APS after you've had, 6.5 million pulses come through. And over here on the right is what you can actually get with tabletops. And this also shows a huge increase as a function of time, 1950 to 2020. This is actually, you can look this up. This is actually a little review article for the 2015, which was the year of light in science. And here is, by John Miao, Ishikawa, Ian Robinson, and Margaret Murnane, all people whom you probably know, right? And so here, their big thing is not really increasing the brilliance as a function of time, but it's actually decreasing the pulse duration as a function of time. So these guys can get below 1 femtosecond in pulse duration. But if you're trying to do, so that is a different regime of extreme, right? But the thing about it is if you want to do some of these flash imaging experiments, you just don't have enough poop in one of those pulses. So the number that you want to remember for a tabletop type source at a kilovolt is on the order of 10 to the 5 X-rays per pulse in a percent bandwidth. So, you won't even say they're really competing with each other in this realm. They're just different and very complementary. So what is it about FELs that are very different from synchrotrons, right? And because we have our synchrotron in the backyard, and it's not going to give you whatever 10 to the 13 photons in 100 femtoseconds. What's different, and they all have the same ingredients, right? You have electron pulses running through through an undulator. So what's different is the fact that the electrons in the XFEL cooperate with each other. and so they can emit coherently because as they traverse the undulator, they actually get into this microbunching mode such that they have little slices of electrons that are separated by a radiation wavelength. So when you take a look at what is the power coming out from the undulator, let's see, it's basically, given by sum over all the electrons of their electric field times their phases squared. And so when you square that, you have this incoherent value here, and then you have this cross term, which you can only extract the power from, this n squared term, if they're actually cooperating with each other. And so this is the big deal with the FEL, and it comes about because you have really, really good electron, very dense electron pulses going through those undulators. So these have captured the imagination of many places, and they're coming up all around the world now. I mean, the LCLS turned on as a hard X-ray FEL for the first time in April of 2009, but now there are all these other FELs coming on, and they come in sort of 7 groupings. And right now, 4 of them are actually operational. There are 2 hard X-ray ones, the one in Stanford, and then also the one in Japan. There are 2 soft X-ray ones, the one Flash in Hamburg and Fermi, which is a rather special one in Italy. And then in the next couple of years, it's a really exciting time. In the next couple of years, right, there's going to be the European XFEL coming up in 2017, the Swiss FEL in 2017, and the Korean PAL FEL. Kwanjay, is it this year or next? It's coming soon, right, Kwanjay? Yes, very soon. Some of these numbers may not be, completion dates are always a little bit nebulous, right? So this is sort of the FEL. So that's the milestone that they pointed out in the Nature crystallography rag. And what you actually do with it is shown in this thing, which is like a poster child for the LCLS. It's single molecule imaging. And okay, so who in this audience has not seen this type of picture before? Really? Oh my God. Okay, so, all right, so the idea is, you take a protein molecule, it's not crystallized, you drop it into this very bright beam. This very bright beam scatters off of all the atoms and electrons in that molecule. You catch the scattering pattern both in the near field and the far field, and from this scattering pattern, the idea is that you can reconstruct in 3D the positions of the atoms in that very complex system. And for an AMO scientist, actually this looks it looks exactly like an experiment you'd do in your lab, except for, you don't have x-rays coming in, but it looks exactly the same. So from an AMO perspective, there are many interesting things that will happen, because remember, to do this, you're in a regime of X-ray interactions that you've never been in before. You're in a regime where it's nonlinear, it's multiphoton, and you have lots of things going on. So for us, right, what's interesting? What's interesting is that, okay, so that picture didn't come from nowhere. That picture was the result of a seminal work by János Hojdú and his collaborators, published in Nature in the year 2000. The idea is they take their lysozyme molecule, which has about 14,000 atoms in it, and they irradiate it with that pulse. And during, say, 10 femtoseconds during that pulse, nothing's actually happening. The atoms are still kind of stuck together. But then after, say, 50 femtoseconds or so, things have charged up a bit, and the thing is falling apart in a Coulomb explosion. And so the idea is that, okay, well, maybe if I make my pulse short enough, then I can capture this diffraction pattern before these atoms have flown apart and gone somewhere, right? That makes a lot of sense. But one of the issues is that even before this Coulomb explosion takes place, there's a lot of electronic damage going on, because the electrons are rattling around inside this complex system, and the electrons are actually what's doing the scattering that you're measuring in the pattern. So from an AMO perspective, it's a really nice thing to be able to know where are the electrons. Okay, and then the actual power density that is achieved inside this spot is on the order of 10 to the 22 watts per square centimeter at 1 angstrom. That is a huge amount of power. So just to put it in sort of perspective, an atomic unit of intensity equal to the binding of an electron to a nucleus, a proton in hydrogen, is around 10 to the 16 watts per square centimeter. So this is like 1,000,000 times greater than that. So it's really, it's very, very intense. And of course, beyond this fundamental nature of X-ray damage, you might like to understand nonlinear X-ray processes. You might like to understand the role of coherence. And of course, if you're an AMO scientist, what you really want to do is have control over what's going on. So you might even like to see if you could do quantum control of, inner shell electrons, something you couldn't certainly never do before. So, in fact, this whole concept was tested in that paper that was shown on in that Milestones rag. And that was looking at a single Mimi virus intercepted an image with an X-ray laser. So this is this Siebert paper. And it was looking at a Mimi virus, which was, about a micron in size, doesn't crystallize, too big for cryo-EM. And they could get a single-shot scattering pattern with 32 nanometer resolution, sort of in 2D. So, that was a good first step back in, well, this was published in 2011, but, the data was taken as one of the first runs. Well, okay, so that's not 3D, and time goes on. Time goes on till, last year at this time. And they took that data set, and they finally managed to reconstruct into 3D. And so here is a 3D reconstruction of that same hemivirus particle. When they were able to take about 200 of these diffraction patterns and orient them properly such that they could actually reconstruct something in 3D to about 120 nanometer resolution. So, I would have to say it's a little bit of a far way to get to atomic resolution from this, as you can see. But okay, that doesn't deter you from going on and doing research, because it's kind of an interesting thing. So, associated with that PRL was this physics viewpoint, X-ray imaging of a single virus in 3D. And this is written by Keith Nugent, someone also well known to all you folks. It basically goes, and there are still open questions on the impact of electronic damage on X-ray scattering in femtosecond timescales. And I'll tell you about, how these things happen in atoms. Okay, now, one other thing is, of course, the LCLS doesn't only do Mimi virus imaging, single particle imaging, right? It does many other things as well. And there's a document, LCLS First Experiments, that has a lot of different topics associated with it. And in the AMO section, we were interested in understanding and controlling X-ray atom molecule interactions at these very high intensities as a foundation for other applications, and also to provide some diagnostics of the LCLS radiation. Okay, so I thought I'd just tell you about this first experiment, because it turns out, when you do a first experiment, you're on a very steep learning curve. You learn a huge amount when you first start, and so that's what I'm going to tell you about, is this our first experiment. And we're looking at the nature of the electronic response to effluents that's 10 to the 5 X-rays per square angstrom, and we could vary the pulse duration from 80 to 340 femtoseconds, and the photon energy from 800 to 2000 eV, and achieve this intensity of 10 to the 18, which, while very high and higher than ever achieved before, was not quite, was a little bit away from the single molecule imaging intensities. Okay, so you have to choose what you want to look at, and we chose to look at neon. Why do we choose to look at neon? Because it's very well characterized. It has the binding energies in neutral neon are, for the 2p and 2s, 20 and 50 eV, and for the 1s has this very nice edge right at 870 eV. And so that's right in between the 800 and the 2000 that we were, told that we could expect when we first started. So, and we also know that upon inner shell excitation, that you'd have an Auger yield of around 98%, and you'd have a clock that was ticking at around 2.4 femtoseconds. So all this is pretty interesting, and so we thought, okay, we're going to probe the changes in the interaction when we go from talking to the outer shell of neon to talking to the inner shell of neon, going between 800 and 2000 eV. Sort of as shown very crudely there. And the first thing that you like to do is you want to be guided by theory. You don't want to go in blindly. You want to know what to expect. And so way before we did the experiment, Robin Santra and Nina Rohringer, who were here in our group, did this theory to predict what would happen for 3 target energies, 800 below the K edge, so you're only talking to the outer shell electrons, 1050 above the K edge and above the hollow atom threshold, and then 2000 eV where you're above all the ionization energies of all charge states in neon. So you're just way above anything that can interact. And what you can see here is sort of a complex series of things. This is showing 6+, which happens by this VVVV, which is a whole bunch of valence ionizations, and so on and so forth. It's easier to see in this picture, very nice picture made by Bertold Kressig in our group, looking at sequential single photon processes. And so this is basically the mechanism by which the X-rays are interacting with the atom. So if you're at 800 eV, you can only talk to the outer shell electrons. And so what you're doing is you're valence ionizing all those outer shell electrons up to neon 8+. If you get at this intermediate energy, 1050, you go through this sequence of photoionization, Auger decay, photoionization, Auger decay, et cetera, until you sort of run into some energy where you can no longer do an inner shell ionization, and then you start doing valence ionizations. And then, at very high energies, you can actually go all the way up in sort of this sequence such that you can strip the atom completely. But that's only talking about charge states. What you'd actually like to know is how it actually got there during the course of the pulse. Because whenever you're doing an X-ray imaging experiment, you're getting the integral of what's happening. So it's not just what happened, where you ended up. It's the integral of everything that was going on. So at low intensities, what would you have? Well, what you'd have is that you'd have a photoionization making a hole here, and then you'd have an Auger decay transferring 2 holes to the 2p, and then you could follow it by another photoionization. But at high intensities, you could have the situation where after the first photoionization, the second photoionization could come before that 2.4 femtosecond Auger decay, such you create a hollow atom, and then you could then further go on to the Auger decay. So how do you distinguish what's going on? Well, it turns out that the electron spectroscopy can easily distinguish hollow atoms because the Auger decay has a much different angular distribution than the photoions, and so you can actually pick out what you want. And so this is the apparatus we used in that very first experiment at LCLS that had a neon gas jet, and then we had these 5 electron time of flight spectrometers where you could measure the angular distributions, and also an ion time of flight. So you can measure all these things simultaneously. And John Bozek and Christoph Bostad, who's now here, were the instrument scientists at the time when we were doing this. Okay, so the first thing, day one, of course it was dramatic for us, but I think it was anticlimactic for everyone who had already been working there. It was dramatic for us to come in. But the very first thing we saw was that a single 100 femtosecond pulse at 2000 eV fully strips the neon atom. And that's a 6-photon, 10-electron process. That all happens in 100 femtoseconds with that pulse on. So it's really quite dramatic. And then the other thing we found out was that shorter pulses with equal pulse energy and fluence suppress the absorption and the damage, which is kind of a funny thing because you think, well, usually when you have something that's much higher intensity, that creates a lot more damage. But here it was the opposite situation. So that was kind of strange. And actually that came about because we could actually tune the X-ray pulse duration from about 80 to around 250 femtoseconds. And what's interesting about that is that, just before everything started, we had a little meeting with the accelerator folks, with Paul, Emma, and Zhirong Wang. And Paul says, would it be interesting to you if we could change the pulse duration? We said, well, of course it'd be interesting to us if you could change, but this was not something that we had known beforehand. And I said, well, how long does that take? He says, oh, it might take 15, 30 minutes, something. Well, of course we want to change the pulse duration. So anyway, it goes to show how much good you can have when you interact with the machine physicists when you're an experimenter. Okay, so this was a little bit mysterious to us. So here's what, so if you take a look here, the red is the 250 femtoseconds, the black is the 80 femtoseconds. And you see that the red is, the longer pulse, the 250, just produces a lot more higher charge states. And that's really weird because A, we're changing this pulse duration over these really long time scales, and it's just counterintuitive, right? But there's nothing you can do because you only have 5 days and you have to keep marching on with your plan, right? And so we marched on with our plan. We looked at 800, 1050, and 2000 EV. And we eventually compared to the theory that Nina and Robin had done. And we found that, we got very good agreement between experiment and theory as shown on here. But we still had this sort of mystery as to what was going on with, the pulse duration dependence. And of course, when you go away and think about it, it becomes obvious. But, when you're first there, it's kind of like, what's going on? So it turns out that, of course, atoms actually become transparent at high X-ray intensity. So, the X-ray absorption, at that 2000 eV where this was observed, it's due to the presence of 1s electrons. If you make a hollow atom, then you've lost that absorption quite a bit. So the mystery is, why is it at those very long time scales? And what happens, of course, is when you're marching out to those high charge states, which is where you actually see the effect, what you see is that the Auger rate is decreasing substantially, such that it gets up to that sort of 100 femtosecond type regime that is important for changing things around. So this became much more obvious when you thought about it a little more. Let's see. Electron spectrometers, I told you, can track the ionization mechanisms. You can focus in on a place where you actually are just looking for the hollow atom yield, and that's shown here compared to the single core hole situation. So you can see it's a very clean signature. If you look at how many you actually make, it turns out that at LCLS you have a yield on the order of 10%. At the synchrotron, you can also make hollow atoms. It's not like they're not known. It's just that they arise from electron correlation, not from a deliberate, kicking out of the inner shell electron by your intense pulses. And so we thought, oh, that's kind of a lot of hollow atoms. And we thought, well, what does that actually do to, what would it look like if you actually had a crystal of like hollow carbon atoms that you're looking at as opposed to, normal atoms? And so we did this calculation looking at the ratio of the photoabsorption cross-section to the elastic scattering cross-section. So here is the photoabsorption cross-section here, and this is the elastic scattering. The elastic scattering, of course, is what you use for all your scattering, for all these diffractive imaging. And so the damage from the photoabsorption is just way higher than any of this, this coherent scattering. And so what we found was that it doesn't have that much of an effect to have the hollow atom versus the pristine carbon. So here you can see that ratio of the bad damage to the elastic is 20, and then for a hollow atom, it's 2. So it's not so bad. All right, so what we learned from all this was one experiment can tell you a lot of things. And what it can tell you is that sequential single photon absorption is the dominant ionization mechanism. It's not some other weird thing that you might just wonder because you have such high intensities, right? And in a second experiment led by Gilles Dumy of our group, we found that direct 2-photon absorption was quite small. We also found that we suspected this induced transparency was a general phenomena, and in fact it was later found in molecules and in clusters and in solids, and it has some implications for imaging because this ratio of the scattering to the absorption has increased. Okay, so we had a nice paper in Nature, and there was a nice news and views on it, which gives you the general feel for what's going on. But here is, I wanted to just emphasize that it was real collaboration between, the AMO group, which is shown here in 2009. I want to point out Steve Southworth. Here's Elliot and Fei Ho, who's still with us, and Anne Marie, who's still with us. And here at AMO Control, because you weren't actually really allowed to go in and dink with everything. It was really the instrument scientists who got to do all that fun stuff, right? And here's Christoph smiling very happily there. And then really the true heroes were these guys over in the main control center who were actually controlling all these, the electron beam, because we couldn't. Well, it's not like here, right? You want a different energy. And the undulators are a fixed gap. And so the only way you can get a different energy is to call the folks in the main control center on the phone and say, I would like a different energy. And so it's not like here where you can, type into your screen and then just change your energy. But I should know, you guys probably all also know that, the 100 meters of undulator that were installed at LCLS and still used there were in fact built here at Argonne. So it's something that, it's a collaborative spirit everywhere. Okay, so what about complex atoms, right? That was a really simple atom. That was neon. Well, in a complex atom, in neon, what do you get? You make a hole and then you get this Auger decay. But for example, if you do xenon and you do a 2s ionization, as you might have at like 5 keV or so, then what you have is, count it, you can have 1, 2, 3, 4, 5, 6, 7, 8 electrons coming out from one photon absorption. So it's a very complex process. And you can track what's going on with that via simulation, the same way we were doing before, right? So what you can see is that when you start out, you have these photoionizations here. They're followed by Augers. When you get up to the higher charge states, then fluorescence starts coming in. And this is for xenon at 4 keV. And you can look at it in a little more detail as photoionization, then these Auger decays and so on and so forth, and eventually you get here with a little fluorescence. Okay, so all this is happening very rapidly. But what is also important to remember is that even though you may think, oh, this is really boring, it's just sequential, ionization, but actually what you can see is that when you look at nonlinear processes, what are you looking for nonlinearities in? So here, typically you look at ion yield versus, intensity or fluence. And what you can see is that you can have these, each of these things is going at a very highly nonlinear rate or nonlinear slope, and that's all due to sequential single photon ionizations. And eventually it saturates when you get to saturation fluence. And all these things are actually all happening on the same time scale, right? So all those Auger decays, they're at like a femtosecond or so, and so all these cascades are happening while your photon pulse is there and while all these other things are happening. So it's a pretty complex process. And what about resonances? Okay, so we didn't even talk about resonances, but they can actually disturb rather dramatically this idea of single photon ionization until you get to some energy where the ion charge state is so high, your photon can no longer, ionize. So it turns out that in argon, let's say you irradiate at 480 MeV. This is actually a PRL where Christoph was one of the authors, showing that sequential single photon limit was 10 plus, but they actually observed 13 plus. So something is going on. And here, at 1500 EV in xenon, the sequential single photon limit is 27, but they observed 36 plus. I mean, that's a pretty dramatic difference, right? And whereas at 2000 EV, it was actually dead on. And these are the things, these sequential single photon limits are the things that are predicted by the code that was, originally introduced by Sankil and Robin, and that's shown down here. So we thought, okay, you really need to take into account these resonances if you want to figure out what's going on, right? And so originally this, okay, first you have to establish that this whole idea even works, that the idea of a cross-section and a fluence actually works to predict what you're going to get. And that does work when this lowest order of perturbation theory does work because in this case, the ponderomotive energy is much less than the photon energy. And so you go through this Hartree-Fock-Slater to calculate the cross-sections and rates. But then for that xenon case that had so many different things, it actually had 20 million coupled rate equations, 2 billion processes, so a Monte Carlo approach had to be made. And then, including resonances, it's an even more massive computational problem. And so Fei Ho here introduced an efficient database plus the Monte Carlo to store and retrieve all the data. And you can take a look at what the magnitude of the problem is to some degree. So if you don't include any resonant excitations, in argon, krypton, and xenon for excitation in those, you're getting to the millions of, tens of millions of electron configurations. But if you need to include the resonant excitations, then you're going up to, in this case, about 10 to the 23 electron configurations, which is a huge number, especially when Fei likes to remind me that the maximum of an unsigned 64-bit integer is only 10 to the 19. So you can't just calculate them all and store them somewhere and go after them. So he did made a very nice way to do that. So then what you can do when you have all this is you can look at those problems where you're going far beyond the sequential single photon limit. And so this is a Sankey diagram showing for the argon case going from 0 out to 12, 13 plus a particular pathway where you have photoionization, Auger, et cetera, all the way out here where this funny little path here in resonant excitations is causing basically 25% of the yield of the argon 12 plus. And here, this inset here shows the difference between counting for resonant excitations and with no resonant excitation. So the experiment is in red. When you include the resonant excitations in green, you can kind of agree, but when you don't include them, you're stuck down at this other limit. Okay, so we were interested also in understanding the difference between seeded and SASE pulses. Actually, these guys who do imaging or these things where you're way above all edges, they don't necessarily care so much about the fact that the FEL does not produce pure Gaussian pulses, but Other people who want to do spectroscopy do care. And so we were looking at the difference between seeded and SAS ionization and the effect of resonance in krypton, and we could produce a nice landscape and figure out where you'll actually have hotspots of ionization and where you can avoid this if you'd like to. Okay, so let me just summarize. Okay, so what did we learn? I mean, why do any of you guys care about all this detail about where are all these electrons going? Well, basically what you now understand, right, is the difference between these ultra-strong X-ray interactions and the ultra-strong optical interactions. In the optical regime, what you have is sort of a single electron multi-photon interaction, stripping off an outer electron. In the X-ray regime, what you have is many single electron, single photon interactions, giving you this, concerted sequential ionization. It's quite different, and something that you will never see at a synchrotron because you don't really have the fluence for that to happen in a single pulse. Also all these rates are happening at the same time. The inner shell, the photoabsorption, the ionization, the Auger, it's all happening on this femtosecond timescale. So it's a very complex process to understand, to model. The multi-photon absorption is actually rather insensitive to these SASE pulses, which you might not have expected if you thought it was a highly nonlinear process. But because it's this sequential process instead, it's really not very, very sensitive. And the continuing challenge is to increase the complexity such that we can look at things and actually model them in ways that are interesting for folks who are trying to do the coherent diffractive imaging. And so this is a nice picture made by Fay, where what you're looking at is, if you want to calculate an X-ray diffraction image that includes all this electronic and structural damage, what you're doing is you have the Thomson cross-section times this integral over the flux contained in your X-ray pulse of the form factor of the nanoparticle as a function of time. What is that form factor of the nanoparticle? Well, it's form factor of the atoms plus that of the free electrons. And the form factor of the atom, of course, includes all of those configurations that we just talked about. And so this is how it all feeds into something that other folks might be interested in. And so how do you actually tackle this for a system that's large enough to be interesting, right? Well, you use a large computer, and you use people with large brains who know how to use large computers. And so here's Fei Ho, and here's Chris Knight, who's part of the ALCF. And so here, the idea was to do this computer simulation of all these experimental observables with atomistic detail. So the idea is that you can, you account for all the processes that I've told you about, and you calculate these observables, the ion charge states, the photoelectrons, the Auger fluorescence spectra, the X-ray diffraction image, and of course then you would like to go back and compare that with experiment. And so these calculations go beyond previous things that were done by Neutze and Zurich. They go beyond electronic damage studies only of Vartanians and Quiney. What they do is a Monte Carlo for the quantum processes, followed by classical molecular dynamics simulations for the ions and electrons after all this stuff has happened. Okay, and what's cool is that it's presently capable of tracking like 50 million particles, which is a huge, huge number. Okay, so here's some pictures of what's going on with the XFEL-induced electronic dynamics. This is a 7-shell argon cluster. It has about 1,400 atoms in it. Here's kind of before, and here's at like 30 femtoseconds. The dissolution of that particle. These are the diffraction patterns coming from an 8 keV 30 femtosecond XFEL pulse, shown here for different fluences, 10, 11, 12, and 13 photons per square micron, which are all attainable. But it really does absolutely no good to calculate things unless you can validate them. So we were lucky that we were actually able to validate this whole process. First, you might ask, well, does this approach even work, right? we're doing quantum calculations for the atoms. We're treating everything as atoms and electrons, and then we're going through with the molecular dynamics code. Well, it actually, recently in 2014, there was an experiment at LCLS on C60, and a theory by Robin Santra and his group that reproduced the ion yields, that's all they measured, and the kinetic energies. So, it's kind of, okay, that idea seems to work pretty well. And it was recently, a new experiment came out just at the end of last year from SACLA, the other FEL that's working, on argon that had like 1,000 atoms to it. And that one only measured electrons. One measured ions, one measured electrons. Okay, but it turns out that the code that Faye and Chris have been doing actually turned out very well to match the experimental data. So the experimental data here is in these blue dashes, and the argon MCMD code is shown here in the green. It matches very well, and in fact, even better than the XMDIN, which is the corresponding code at DAISY. And the reason for this actually is the fact that Faye included in his code recombination, and they didn't at DAISY. So it of course is also no good if you just calculate diffraction patterns. You also have to reconstruct the diffraction patterns. And so here we have a collaboration with Miklos Tegzi and Julia Feigl in Hungary to be able to do that. And so here again is the 7-shell argon cluster. We looked at an ideal case with a 2 femtosecond pulse, got a complete Q-space map in 3D, and they were able to reconstruct, even at those high fluences where the pattern was starting to look a little bit washed out, right? So here we have 10 to the 15 photons per square micron, which is a very high intensity, and this is the radial average of the scattering, and that's this last one here. But here you can even still see sort of, the atomic level structure in this icosahedral argon 7-shell structure. Okay, but it's nice to have all this, but you really need data that encompasses all this. And so what's cool is that now Christoph is here, and he actually has been working on combining spectroscopy and imaging of clusters so that we can get both the image and all this ion electron information. And so that's what's shown here. Well, it's a standard apparatus, but what you can see is if you can do it on a single shot basis, this is what the ion time of flight looks, the ion distribution. If you actually did average, because the particle could be not in the center of the beam, it could be elsewhere, right? And so you wouldn't necessarily get the same ion distribution. So the top one is single shot imaging, and then down here is where it's averaged. But you can also actually tell by having also the scattering pattern, the fluence and the size of the cluster from the scattering. So you get the fluence by the integrated, intensity, and the actual size by these, minima in the scattering pattern. So in this way, you could, in principle, actually have all the, electron, ion, and scattering data that would then be fed into, the computation, which I think is just really cool. And I want to point out that this actually was the thesis of Thijs Gorkover, who's going to be coming as an argon, as a Fermi fellow, right, in about a year. And she was been working with Christoph, and Christoph recruited her very, very well. So what is it so why are we going to the extremes? I just wanted to show this picture, and you've probably seen it many times before. It compares light source evolution and computational evolution. And what I want to say is that we're going to sort of the extremes on both of these. Here is the LCLS in terms of brilliance. Of course, light sources are going up faster than computation, but all right. And here, roughly, is the Blue Gene Mira machine. But, we're making use of all those good things. Now, at LCLS, they aren't standing still. I mean, everything I showed you was basically SASE, self-amplified spontaneous emission, data. But they are doing many other things. We know that they developed hard X-ray self-seeding. actually in collaboration with Argonne, with Sasha and Yuri and a number of other people. They've also developed soft X-ray self-seeding, as shown here, which is exactly the same principle, except for the fact that it's much more complicated than the diamond monochromator to get the soft X-rays. But up here, you actually have 2-pulse, 2-color possibilities at LCLS now. And here, what it's shown is the little chicane section that was used for self-seeding is actually also useful to make 2 pulses. So you have one pulse going through the undulator, giving you this blue pulse, and then you can, chicane. You can take the electron, and that's giving you some sassy pulse. Then you can take the electron beam and put it through a little bit of delay and send it through the undulator, which might be at a slightly different K because although they're fixed gap, they are tapered, so you can have like a 2% change in the wavelength. And you can also have this other method, which was also reported recently, where you can create 2 electron bunches, which create 2 X-ray pulses at different colors because they're accelerated at different times in the RF. And so it turns out that the AMO group was actually the first to use each of these two color, two X-ray pulse situations. This top one was led by Christoph, and what we have here was in the hard X-ray range. We have X-ray pump, X-ray probe at like 8 kV. And here the idea is that, okay, you damage your thing with the first X-ray pulse, and you can probe what happened with the second X-ray pulse, right? So what you have is something that's a little bit above the copper K edge coming in to damage the pulse, and then the xenon cluster, which was about 3 million atoms. And then you can come in with a second probe pulse to see what happened. The first pulse is absorbed by this copper screen, and the second pulse goes through, and you can capture it on the detector. And so this was a very nice experiment that observed a surprising lattice contraction of about 3% happening in 80 femtoseconds, which is unusual because basically all theories show an expansion, right? You see all this Coulomb explosion expansion business. And so that was published in Science Advances earlier this year. You could look it up. And then the other was in the soft X-ray range, led by Antonio Picone and Steve Southworth. And this one is looking at a much smaller molecule. And here what you do is that this is in the soft X-ray range. And so you pump with 690, liberating a 3D electron from the xenon atom. And then you probe with 683, which is looking at one of these fluorine atoms as it dissociates. And so this one is basically monitoring inner shell hole dynamics, and it was the very first time when you could actually observe this on this femtosecond time scale, the transfer from one to the other. Okay, so let me, okay. There's been nothing about APS yet, so I want to say something about APS. It'd be bad if I didn't say something about APS, right? So of course, everyone knows that they're complementary. And that if you actually want to watch dynamics, and not all interesting dynamics happens on the femtosecond timescale, you can watch it really well here at the APS. And typically, when you want to watch, dynamics with an X-ray pulse, you'd like it not to be doing all these weird things. You'd actually like it to be a nice linear process that you're looking at. And so it turns out because you have this very stable, high rep rate source out there, you can couple it with a very stable, high rep rate excitation source, and then you can start to observe transient signals with the same fidelity as the ground state, which is kind of cool. And so you know that this is really, really made for APS because we have this very nice pulse structure in the ring. That large interval between pulses, in addition to enabling Mossbauer spectroscopy, also allows mechanical chopping of X-rays, sample relaxation, sample replenishment, and pixel detector gating, so it's really good for timing experiments. So, of course, if you're only looking at elementary processes, you may only be interested in, these things up here. But there are many other interesting things that in chemicals, proteins, liquids, and solids that are on the time scales as shown down here. This is microseconds, nanoseconds, picoseconds that are accessible at the APS. So one of the pioneers of this whole idea was Lin Chen, and this is one of her slides showing, let's see, we're going to excite our molecule from the ground state into some excited state, and we're going to probe as this thing, traverses its landscape down to somewhere, right? And so what the AMO group has done has, used that idea, but just implemented it at high rep rate and implemented more spectroscopies beyond just X-ray absorption. Okay, so primarily Anne-Marie Marsh, Gilles Dumy, and Steve Southworth made an optical pump X-ray probe setup at the APS where you could simultaneously look at X-ray absorption, X-ray emission, and X-ray diffuse scattering. And that's kind of shown here. And it was implemented with a laser that can run at a very high rep rate commensurate with that in the ring. And so, let's see. It's particularly nice to have both the X-ray absorption and the X-ray emission. So the X-ray absorption is shown here, and the X-ray emission is shown here. And the X-ray absorption is sensitive to the unoccupied states, and the X-ray emission to the occupied states in your atom or system. But your laser that you're playing with actually bridges these two. So now you can watch the two while you're playing with your stimulating system. And of course, because you have hard X-rays, you can look at any media, liquid, solids, gases, in situ. It's element specific. It has electronic structure sensitivity with valence orbitals and spin, geometric structure from XAPs, and so on and so forth. So here's a nice picture of how you can actually get really excellent statistics this way, right? And this is due to the high rep rate and stable system that we have. And so this is looking at the emission spectra of this particular system. And here we have the APS data that was acquired in 1 hour, shown here in blue. And then here we have the same system looked at the Swiss light source with a kilohertz repetition rate after 1 week. And so after seeing that, the first time that Georgi Vanko saw that, he just kept coming back time and time again. You can imagine why, right? And so, let's see. So in fact, very recently, what we've done is instead of that very first one was done with just a Johann geometry and a single crystal spherical analyzer, but in fact, Georgi and the team at APSCol with Wojciech Gavalda came back and brought this nice von Hamos X-ray emission spectrometer, where you can map the K alpha, which is what people almost always look at, the K beta, which is very sensitive to spin state, but also the valence to core transitions, which are very interesting for looking at dynamics and other things. And so with this von Hamos spectrometer, you can actually get the entire spectrum simultaneously, and that was just done at Sector 7 last week. And for X-ray diffuse scattering, what's interesting is the scattering signal that you get in the forward direction can be decomposed into components from the solute, solvent, and cage, and from it you can deduce structure, temperature rises, density changes, and from that we were able to figure out that, in fact, in a particular system, what the solvent shell looked like around it. So what is a very typical system to look at have been these spin crossover materials, where it goes typically, it starts out in a low spin state. This would be iron 2+. And you can manipulate it into a high spin state by light or temperature or pressure. And the high spin state is much larger than the the low spin state, and it has many other changes in properties. So it's been very interesting from an applications perspective. In fact, there are books written on this sort of thing, which I didn't know until I was looking at this. And I found out another interesting thing. Turns out that Michel van Veenendaal is, in fact, quite an expert in, well, he's written several, like PRLs and stuff, on how you go from the low spin state to the high spin state. So how do you go from a singlet to a quintet? That's like, it's kind of an interesting, mechanism. And so this is a nice system to look at. And, a first experiment that was done here was looking with simultaneous, all these spectroscopies. And what you do is you excite up into this metal ligand charge transfer state, and it somehow gets over into this quintet state. The idea is to characterize this mechanism. And from this particular situation, we confirmed, from this particular experiment, confirmed that the metastable quintet state was consistent with this very large 0.2 angstrom expansion from the ground state, and that it had this 600 picosecond lifetime, which you can actually see here very nicely. So the idea is to have that very long-lived state. And recently at LCLS, these findings were confirmed on the 1 picosecond time scale by Christopher Haldrup and his collaborators. Also, this X-ray emission spectroscopy is rather powerful. Recently, that triplet state was kind of hard to see because it's very short-lived. And so with some femtosecond X-ray emission spectroscopy at LCLS, you could actually, you could infer the presence of this triplet state as shown in this slide because, well, it's a lot of modeling, but in any event. And with very high precision, as you can get here, you can actually start to deduce very slight changes in some of these high spin states. And this, instead of looking at the prototypical BIPI molecule, this was looking at iron terpy, which is a tridentate ligand and actually breaks the symmetry such that the quintet T state turns into an E and a B. And it turns out that with the precision XFs, you could actually isolate that this quintet E was the actual ground state, which is something that wasn't known before. So, this sort of thing is interesting to many, many people. And so these are the people shown on this slide. And so at Argonne, there are a bunch of us who are sort of interested in pushing this forward. And the European APSCol guys, they're going to put basically the simultaneous, all these spectroscopies and scattering in on their X-ray pump probe station. So they brought it here. Well, they've been here many times, like I said. And so they brought it here to test. George Vanko is really the expert on X-ray emission spectroscopy, and he's been here many times because it's obviously the best place to go. And Christopher Haldrup and also. And then these folks over here, like there are many folks who are interested in these spin crossover complexes. And all these guys have come for that and photocatalysis. But let's see, so what do I want to say? So beyond what we're doing, there are many other applications for time-resolved spectroscopies and scattering. There's quantum materials, and people like to manipulate 2D materials and others to understand and control emergence of collective behavior and do light-induced phase transitions between various states. And also, of course, surface chemistry watching charge transfer and whatnot. And this is a little bit, in some sense, this is a little bit, you're a victim of your own success because now all these people are coming and they want to use the lasers. And so now, like Anne-Marie and Jill are always helping folks use lasers, which is nice, right? but it's very nice. And also, I should note that even scientists here at the APS are quite interested in this. I was talking with Hayden earlier, but John Freeland's interested in time-resolved XMCD, and Hayden is interested in terahertz pump X-ray probe microdiffraction experiments. So all these things are, they're very interesting, and they're very suited for the machine you have here. Okay, so now I'm coming back to answer Stephen's question. What is it that we do, right? So here's what we do. So we'd like to have a quantitative and predictive understanding of X-ray matter interactions in this ultra-fast, ultra-intense regime. That was the first part of what I was talking about. We also like to understand ultra-fast inner shell phenomena. And in that quest, we make use of these very advanced X-ray capabilities that are being now developed at APSCol. And then, of course, we have these X-ray probes of laser-induced dynamics that are done here. And it's all, I would say, it's all a lot of fun. And so I want to leave you with this picture of a very, very our group. And so anyway, thank you for your attention. I'm sorry, I think I ran late.
All right, questions for Linda?
No questions.
Saturated them. Actually,
I saturated them.
I'll get back to Jerry in just a second. So I do have one question, taking the chairman's prerogative first.
Yeah.
So there was a crossover at about 10 to 14 photons per micron squared before you started to lose the structure in certain systems. Is there something universal about that fluence? Or is that really dependent on the absorption cross-section as a function of energy?
No, I wouldn't say there's anything magic about 10 to the 14 per square micron.
Yeah, it's, when you were doing the reconstruction of the images with the APSCol pulse, there was a certain fluency you got to where the particle basically started to fall apart and you started to lose the atomic positions.
Yeah, no, I wouldn't say that there's a magic fluence for any of these things.
Okay.
Of course, it's enhanced when the absorption is enhanced, right? So the higher energy you go, the system can, that's all related to damage, which is all related to absorption. So that's all related to the absorption cross-section of the system of interest. So the system we were looking at was argon, which is Z18, right? But it would probably be better for biological systems, which have carbon, nitrogen, and whatnot.
Okay. Jerry.
A lot of work going on behind the scenes to do those experiments.
Yeah.
I probably have hundreds of questions, but the one that early in the talk, the question, just when you look like you were dropping a protein molecule. I mean, it's not that simple, right? I mean, you don't just drop a protein molecule through the beam. So, how do you do that?
Well, actually, there are many ways to do that. The way that it's done for protein, there is kind of twofold. One is sort of a water jet that has been, many versions have been explored, I would say. They first thought they would have jets with little droplets, but now they found it's better just to go in a continuous fashion. The cluster jets, those are pulsed valves with skimmers, like a normal molecular beam. They also have toothpaste injectors because, in fact, you waste a huge amount of your product because, your X-ray pulse is on for 100 femtoseconds, and then you have to wait another 10 milliseconds before another one comes. So the duty cycle is like very low. So then they have something that goes very slowly called a lipidic cubic phase injector. So there are so many ways to introduce targets into the beam. It's that's probably the hardest part.
Yeah. Okay. Thanks.
Other questions for Lynn?
Okay.
All right.
No questions.
Thank you very much. It's
Thank
fascinating.
you.